Okay, so we're going to be covering section 2.3, and this is all about functions. So first of all, we're going to define what a relation and what a function is, and then we're going to look at a bunch of different cases. So we say a relation is a set of ordered pairs. And a function is a type of relation. So a function is a relation in which for each distinct value of the first component, so this is a relation for which for each distinct value of the first component, there is exactly one value of the second component. I should say of the ordered pairs. There is exactly one value of the second component. Okay, so any collection of ordered pairs defines a relation, and a function is a special type of relation where each of the first component is paired to exactly one of the second component. So first example we're going to look at, they're going to give us a couple of point collections, and they're going to say which of these relations. So these are collections of ordered pairs, and we want to decide is the first ordered pair only paired up with exactly one element of the second ordered pair. So let's take a look at these and try to figure out if these relations are functions. We got -4, 1. Okay, so if we look at this first function, 1 gets sent to 2, -2 gets sent to 4, 3 gets sent to 4. So each input is sent to exactly one output. It's okay that -2 is sent to 4 and then 3 is also sent to 4, because -2 only got sent one place and 3 also only got sent one place. For this one here, 1 is sent to 1, 1 is sent to 2, 1 is sent to 3, and then 2 is sent to 3. This one's not a function. The issue here is 1 is being sent to multiple outputs. So you have a single input 1, and you're trying to send it to 1, and you're also trying to send it to 2, and you're also trying to send it to 3. So this right here, this is bad if you have a single input going to multiple outputs. That's what causes the issue with it not being a function. As long as the input goes to only one output, then it's okay and it is a function. So over here we got -4 goes to 1, 2 goes to 1, and 2 goes to 0. So this is not a function. The issue here is 2, trying to send it to 1 and trying to also also send it to 0. So you have one input being sent to two different outputs. That causes the problem. So next they're going to give us a couple of things where they want us to find the domain and range. So the domain, what the domain is, this is the set of all values of the independent variable. And that's usually going to be x. And the range is the set of all values of the dependent variable, which usually is y. So what they're going to have us do in this next example is they're going to give us a couple of expressions. They want us to know, is it a function? What's the domain? What's the range? So we want to answer, is it a function? What's the domain? And what's the range? So part A, they give us 3, -1. They give us 4 and 2. They give us 4 and 5. And they give us 6 and 8. So they use this representation of ordered pairs. In part B, they make what's called a mapping diagram, which is another way you can kind of represent ordered pairs. The x's go over here on the left. So x's are 4, 6, 7, and -3. And those are being sent to numbers 100, 200, and 300. So 4 is sent along to 100, 6 gets sent to 200, 7 also gets sent to 200, and -3 gets sent to 300. And the last one is we have a table of values, so representing the ordered pairs as a table. So we have -5, 0, and +5, and they are all being sent to an output of 2. So for the first one, we want to say, is this a function? So 3 is sent to -1, 4 is sent to 2, 4 is sent to 5. So right there we have a problem. No, this is not a function. The issue is the input 4 got sent to 2 different outputs. It got sent to 2, and then later on they tried to send it to 5. And that causes a problem. You have one input with 2 arrows coming off of it. So one input's going to 2 different outputs. The domain of this, you just list all the x's. Since we have just 3, 4, 4, and 6, you list all the x's, but you only list them once. So even though 4 was 4 and then 4 again, you kind of think the number is either on the list or it's not. So the domain is 3, 4, and 8. Or sorry, 3, 4, and 6. 6 is the x value. Those are the allowed x's. For the range, we have -1, 2, 5, and 8. So -1, 2, 5, and 8. Those are the allowed y values. And that is answering whether that one's a function, what's its domain, what's its range. For this mapping diagram, we want to say, is it a function? So 4 gets sent to one place, 4 is sent along to 100. 6 is sent one place, 6 is sent to 200. 7 is sent one place, 7 sent along to 200. And -3 is also sent to one place, -3 is sent to 300. So yes, this is a function. The domain is the collection of all x's, which is 4, 6, 7, and -3. And the range will be the collection of y's, which in this case is going to be 100, 200, 300. And so that is our answer to that one. And over here we got, okay, -5 gets sent along to 2, 0 gets sent along to 2, and 5 gets sent along to 2. So yes, this is a function. It may seem like it shouldn't be, but if we kind of draw what's going on here, -5 is being sent to one place 2, 0 is being sent to one place 2, and +5 is being sent to one place 2. So for each input, it's being sent along to exactly one output. We don't have 2 arrows coming off of any of the inputs. If I tried to come down here and say like -5 is sent to 7, then that would cause it to fail to be a function, because then there would be a second arrow coming off of -5. But as is, this is fine. It's a function. The domain is going to be the collection of the x's, which is -5, 0, and 5. And the range is the collection of y's, which all the y's are 2. So the range is just 2. Okay, so that is a bit about domain and range. So next they want us to do domain and range from graphs. So they want us to say, find the domain and range. And they're going to give us 3 graphs to look at. First graph is a parabola that comes down to x value 2, y value 1. Second graph is kind of this ellipse shape that goes up to 3, down to negative 3, and then it goes over to 2 and over to 2. So it's kind of hard to draw, but it's kind of like that. And it passes through each of these points. The third one is going to be made up of a couple line segments. So we'll have closed circle here to open circle here. And then down here, we'll have closed circle down there, up to closed circle here. Okay, so we just want to find the domain and range on these. For the first one, the domain, for every single x, since this function extends forever to the left and forever to the right, for every single x, the graph exists, which the domain is a set of x's where it's paired up with a y. And for each x, if you figure out where it hits the graph, each x is paired up with the y by the graph. And so on this parabola, every single x value eventually hits the function somewhere. So its domain is all real numbers. Kind of think of the domain for a graph, it's the x values where the graph is. For the range, this graph doesn't exist. It's basically the y's where the graph is. This graph starts existing here at 1. And then for all the values bigger than 1, the graph exists. So the range would be 1 on up to infinity, we could say. Over here, this domain is the set of x's where the graph exists. The graph starts existing here at negative 2. It exists all the way till you get to positive 2. And so the domain of that is negative 2 to 2. Those are x's that are paired up with y values, and the graph is what pairs them up. So saying the domain is a set of x's where there is a y value is the same as saying the set of x's where the graph exists. The range, we go from negative 3 to positive 3, and the graph exists everywhere in between there. So we'll say negative 3 up to 3. Now here, the x's start existing out here at negative 3 with a closed circle. So that means for the domain, we would have negative 3 with the square bracket. You exist along that line segment till you get here to negative 1 with an open circle. So that'll be negative 1 with an open bracket. Then there's a gap, and you start existing at 2, the closed bracket, because there's a closed circle, up to 3 with the closed bracket, because there's a closed circle there as well. So this is your domain. Your range is kind of a similar idea with the y's. What's the region of y's where the graph exists? So we start existing down here at negative 2, and we exist till we get up to negative 1 on this bottom line segment. Since that has closed dots, we use closed brackets. We use a square brackets in that case. Then there's a big gap. So from negative 1 all the way up to positive 1, nothing's there. Then at 1, we pick up again here, and we exist all the way till we get to 2. So from 1 up to 2, 1 starts with a closed dot, so we get a square bracket. 2 is an open dot, so we get an open bracket. Okay, so that is how to find domain and range graphically of a couple of these. Next, they want us to talk about something called the vertical line test. So the vertical line test, what this says is if every vertical line intersects the graph of a relation, at no more than one point, then the relation is a function. Okay, so they want us to use a vertical line test, say, is it a function or not for this next example? So we're going to start out with a diagonal line. Next we have kind of an ellipse shape. Next we'll have a parabola. And then finally we'll have a parabola but kind of tilted on its side. So for the first one, every vertical line I can draw on this diagonal line, every vertical line will hit the diagonal line only once. So yes, that's a function. I can't find a diagonal line or a vertical line that hits this graph twice. For the second one, I can find a vertical line that when I draw it through hits the function in two different points. So this one here is not a function. I can find a vertical line that bumps into the graph twice, so it's not a function. Third one over here on a parabola, every vertical line I can draw on the parabola will only bump into the parabola once. So yes, this parabola is a function or defines a function. And then out here on this parabola on its side, I can find a line that hits that parabola twice, or the parabola on its side. So no, that's not a function. Okay, so the next bit that we want to do is, what if instead of these kind of easy to work with drawings and graphs and representations, what if we only have the equations and we don't necessarily know what they look like? How does that work? So this example here is going to be kind of the tricky one from the section. They want us to find, is it a function? They want us to say what's the domain and what's the range. So part A, they give us y equals x plus 4. In part B, they give us y equals square root of 2x minus 1. In part C, we get y squared equals x. In part D, we get y is less than or equal to x minus 1. And then down here in part E, we got y equals 5 over x minus 1. So to think of this as a function, you need to think, can each x value that you input, will it always be paired up with exactly one y value? So if I input an x value, what happens to it is I add 4 to it, and then that pairs me up with the y value. And for every x value I can think of, if I input a decimal and add 4 to it, I always get a single decimal back. There is no decimal that I can input, add 4 to it, and get two different answers back. So for this one here, yes, this is a function. Each input that I can input for x will always give me back one output. And then for the domain and range, we could note this is a diagonal line, so its domain and range will be all real numbers. But we could also think for each x value that I put in, if I add 4 to it, that always gives me back another decimal. So this function is defined everywhere because all I'm doing is adding 4, and I never get division by 0, or I never get imaginary numbers back from just adding 4 to a decimal. Also for the range, any number I can think of, I can always choose an x so that if I add 4 to it, it hits the number I'm thinking of. So for the range, I can get all real numbers back as well. Now, for this next one, we think about, okay, is it a function? If I input x, the first thing that happens is it gets multiplied by 2. And if I give you a number and say multiply it by 2, there's only one way to do that, so you only get one answer back. Then I subtract 1 from it, there's only one way to do that. And then I take the positive square root of it, and there's only one way to do that. So each x value that gets inputted, there's a multiply by 2, subtract 1, take the positive square root. there's only one way through that. So each x value gets paired up with one y value. I never give you a number and you multiply it by 2 and you get two different answers back. So that part's not too bad. The tricky part here is going to be the domain. In this case, we don't want x's that cause imaginary numbers. So if we think about it, square roots of negatives cause imaginary numbers. So we're going to take 2x minus 1, the thing we're trying to take the square root of, we want that to not be negative. Because if that is negative, if 2x minus 1 is negative, then when I take the square root of it, I get imaginary numbers back. So if you're not negative, then you're positive or you're 0. So I'm going to set 2x minus 1 greater than or equal to 0. Then I can solve this for x, and that'll tell me what x's are okay. So as long as x is bigger than or equal to a half, 2x minus 1 will be positive or 0, and I can take the square root of positive numbers, I can take the square root of 0, and I avoid the situation where 2x minus 1 is negative, which causes square roots of negatives, which causes imaginary numbers. For the range, I think, okay, if I input all the x's greater than or equal to a half, what y values do I get back? So if I input a half, that gives me back 0. If you think about it, if I input any number bigger than a half, that'll slowly fill out the positive numbers. So as I put numbers that are bigger and bigger and bigger than a half in, I get back y's that are bigger and bigger. So I end up getting, my range in this case would be 0 out to infinity. Okay, this next one. This one is not a function because if I let x be a number, like let's just say 4, then there's two different y's I can solve this equation with. If x is 4, y equals 2 would solve this because 2 squared is 4, and y equals negative 2 would also solve this. Basically, if you all see any operation on the y's where it's y to even powers or absolute value of y, those are almost never a function. For the domain, well, if we think about, since y is being squared, if you square a negative, it becomes positive. If you square 0, it's 0. And if you square a positive, it stays positive. So the x's I'm allowed, since they're equal to y squared, and after you square stuff, you get back 0 or positives. The domain is just going to be 0 and positive numbers. There's no number that's a decimal that if I square it gives me back a negative number. Squaring a negative always goes positive, squaring positive stays positive, and squaring 0 is 0. So that's the domain. The range, I can input anything because when I square them, negative square go positive, so that matches up, and positive squares go positive, and 0 squared goes 0. So I can input any y value here, and the equation is solvable. All right, so for this one, this is not a function, and how we can kind of do this, let's just choose an easy to work with x value like x equals 4. So if we look at x equals 4, the equation becomes y is less than or equal to 4 minus 1 is 3. So x equals 4 is being sent to every y less than or equal to 3. And there's infinitely many y's that are less than or equal to 3. So you're trying to send x equals 4. You're trying to send it to every single y, like, 0 is less than 3. 1 is less than 3. Negative 5 is less than 3. Negative 7.23 is less than 3. Basically, the input x is being sent to every single y value less than 3. There's infinitely many of them, so no, it's not a function. For the domain, any x value you can think of, you subtract 1 from it, and then your equation is y is 1 less than the x value you're thinking of. That is always solvable. There's always some y value out there smaller than the number you're thinking of. So the domain is all real numbers. Regardless of what x you put in there, there's always at least one y value out there that will be small enough to make the inequality true. For the range, any y value you're thinking of, there will always be some x value such that if you subtract 1 from it, it will make the inequality true. So the domain and range in this case are both our real numbers. Then the last one we're going to look at of these parts is this one here. So if I input an x, I subtract 1, there's one way to do that, and then I get 5 divided by the result, and there's one way to do that. So this one is a function again. The domain, as long as I don't get division by 0, everything is going to work out right. So I just need to skip x value equals 1 causes division by 0. So I just need to skip 1 in my domain. And if I input all the numbers other than 1 into this expression, if I input the set here that goes down to negative infinity, I'll fill out, it'll be 5 over negative numbers. If I input the set here 1 up to positive infinity, it'll be 5 over positive numbers. So I can get all the negatives and I can get all the positives. I just can't get back 0, because when you have a fraction, let's say a over b equals 0, if you wanted to solve that, the b would multiply up and you'd get a is 0. So a fraction equals 0 when the top is 0. The top of my fraction here is stuck at 5, which is not 0. So the top could never be 0. So the range, I can get back anybody except for 0. Okay, let's see here. So to finish off this section, we got to talk about function notation, which function notation will write down a quick function. This is a notation where you all use like f of x equals x squared minus 2x plus 1, something like that. That would be function notation. This is the function name. This is the independent variable. And this is the function equation or the function's rule. They want us to find, in this situation for that function, they want us to find f of 2, f of 0, and f of a plus 1. So f of 2, to find that, all y'all are going to do is you're going to replace the x's in the function here with 2's. So what we do is we say, all right, this is going to be 2 squared minus 2 times 2 plus 1. 2 squared is 4. This will be 4 minus 2 times 2 is 4 plus 1. 4 minus 4 cancel, and we get 1 back. So then for f of 0, this is going to be 0 squared minus 2 times 0 plus 1. 0 squared is 0. Negative 2 times 0 is minus 0 plus 1. And we happen to just get 1 back again. So if I wanted f of 3, I would replace the x's with 3 and would solve it out. When I want f of a plus 1, I replace the x's with a plus 1's. And then I simplify it out. I don't solve for a though, because they haven't told me anything about what that function is equal to. So my answer is actually going to be an equation involving a's. So I'll FOIL that term out. That'll be a squared plus 2a plus 1. The negative 2 is going to distribute here, so I'll have negative 2a minus 2. And then we'll have a plus 1. So when we total that up, we get a squared. The positive 2a and the negative 2a cancel. And we get 1 plus 1 minus 2 is just actually ends up being just a squared. Normally you end up with, or it's possible to end up with, you know, a squared, and maybe if the a terms don't cancel out, you have like a plus, you know, 3a plus some other number. But in this case, everything canceled out except for the a squared term. So next bit, they say if we have x minus 2y equals 4, they want us to write this in function notation. This is our next example. Write in function notation and find f of 2 and f of a. So to write this in function notation, first of all, we have to solve this for y. So I'm going to subtract the x across. Then I need to get the y completely by itself, so I have to divide everybody here by a negative 2. So this will give me y equals negative over negative is positive. We get x over 2. And then positive 4 divided by negative 2 is negative 2. So to write this in function notation, you just replace the symbol y with f of x. So f of x is x over 2 minus 2. So this is my function notation. Then I want to find what is f of 2. So to get f of 2, I plug 2 in for x, and I get 2 over 2 minus 2. This is 1 minus 2, which is negative 1. And then if I want to find f of a, I replace x with a, so I get a over 2 minus 2. And that one I just leave. There's not really anything else I can do to simplify that. So that is getting the equation in function notation, and then finding a couple of points like f of 2 or f of a. So the last thing in here we're going to talk about is increasing, decreasing, and constant functions. So we're going to say as you move across the graph, as you move across the graph from left to right, a function is increasing if the y values get larger. A function is decreasing if the y values get smaller. And a function is constant if the y's stay the same. So what we're going to do is we're going to draw a picture of a graph, and we're going to label where is it increasing, decreasing, and constant. So for this example, suppose we have a graph like this. So it starts here at negative 1, 0, and it's going to get from here over to here. Once we reach there, we do the same thing for from here out to here. We go up again, and then we go down till we hit out here. So we think about if we move across the graph from left to right, in this first region here, the y's are getting larger, so our function is increasing. In the middle region here, the y's are staying the same, so we're constant. Out here, the y's are getting larger again, so out on this third segment, we're increasing again. And finally, over here, as we move from left to right, the y's drop, so we're decreasing. And so if we wanted to label where is this graph increasing, decreasing, or constant, we're going to use open brackets, and we want to just indicate the region of x's where the following thing is happening. So for increasing, we have from x equals 0 all the way up to x equals 2. This region of x's here from 0 to 2. This is one region where we're increasing. And then again out here, so this is 2. Out here from 4 up to 5, looks like. For x's in that segment, all the y values as you move from left to right across them get larger. For decreasing, for when we want to find a segment decreasing, we just say, okay, this segment here from 5 up to 6, those x's from 5 to 6, the y values drop over that region, so you're decreasing there. And then finally, where we're constant, that would be from x's 2 all the way up to x's 4, so that would be from 2 up to 4. So when you go to actually answer these, if you want to know where a function's increasing, decreasing, or constant, you state the region of x values for which the function's doing what you want. And that's going to wrap up section 2.3, so we're going to stop there on it, and then we'll record section 2.4 and get that done here in just a minute.